Hello, welcome to my space station. So, I'm sure you would have heard of Willow. Now, if you didn't, then it's probably that you're not being updated on matters that concern quantum computing. But for those who aren't, this video is especially for them. So, what exactly is Willow? Well, Willow is a quantum chip manufactured by Google, which was released in late December 2024. Now, the field of quantum computing is a slowly developing field, right? You don't see as much breakthroughs in this field as you would see in other fields, right? So because progress is slow paced, right, it takes a lot of time, and quantum computing as a concept is generally new to us. We are just beginning to understand how we could implement it, how we can implement quantum mechanics into making our computers better computers. So why is Willow such a breakthrough? I mean, Google released Sycamore in 2018. It didn't hit that much. Why is Willow specifically so amazing? It comes with the advanced technology that Willow employs to do stuff that really nothing else, no classical computer can ever do. Now, that's what sets a quantum computer and a classical computer apart. A classical computer is not that powerful. I think I've already discussed the inner workings of quantum computers, what sets them and classical computers apart in previous videos of mine in which I explained quantum superposition, quantum entanglement, and interference. So basically, I won't be going into too much detail on that, but I'll just give you a recap. Basically, in quantum computers, there are qubits, and those are basically bits that can hold one, zero, or both at the same time. That's what sets them apart from your classical bits in your computers or the mobile that you're watching this on. Your classical computer's bits can only store 1 and 0, but not at the same time. Your bit is either 1 or either 0. Thing is, in a quantum computer, a bit can be either 1, either 0, or 1 and 0 at the same time. Now, the inner workings of these are pretty complicated and have been discussed in my previous videos. So, what was the breakthrough in Willow? Now, obviously, making a quantum chip is pretty impressive by itself. But what set Willow apart from different chips? Well, it was the quantum error correction. Now, in this quantum world, when you have qubits, right, they do not retain this state for too long. Let's say that you give them a superposition and you want the superposition to come out as 1. Sometimes the superposition may come out as 0. That's the concept of quantum computing, probability. So when you get a probability that you do not expect, now it's up to the computer to fix that error. Now this error correction is very, very hard. That's why Sycamore did not hit it. This error correction was basically a flop. It did not correct errors as much, and so it was not able to perform tasks that efficiently. That's why they had to downgrade it, and that's why the benchmarks released by them showed that it did that task in more than 100 seconds. That would take a classical computer 10,000 years, which is pretty impressive. I mean, that is pretty impressive, but we could do better. With Willow, according to Google, has completed the random circuit sampling task, which would take a normal classical computer 1 to the power of 26 years, which is a lot. It solved that in under 5 minutes. And that is something which is truly impressive. So what exactly is random circuit sampling? Well, the deep workings of this are pretty complicated, but what exactly it does is that the computer has a few quantum qubits, right? And some specific randomized collection of gates are applied to it. This qubit is passed through some random gates, right? And then the output is recorded. Now obviously we have classical computers, they also make simulation of this. So we compare the outputs that we get on, like we do a lot of these tests, and we compare their outputs to the expected outputs. Now the more different they are, the more errors that chip has. Now completing RCS meaning it means that you got all of them correct. Now it takes a lot of time and a lot of tries, and the benchmark released by Google obviously states that it did it under 5 minutes, okay, which is pretty impressive. Okay, random circuit sampling is not really a task which has any real world applications, right? It is just there to make a quantum computer prove that it's a quantum computer. It's like it's not a task that has any real world value. Obviously it is just pretty hard and it's very complicated, and if the chip is able to do it in an okay amount of time, it means that it's pretty powerful, and it means that it sets it apart from the other quantum chips that have been produced. Now, how do you correct these errors that will appear eventually? They are inevitable. They will appear in these quantum systems. Now, there are different ways that you use to correct them, and the inner workings of these have not been fully released to the public. So, this is more a matter of speculation about how Google corrected these errors. But the main idea, the basic idea behind them is that, let's say you have a qubit, right? And there's an error in it. Now, you will use the qubits around it. Basically, when your qubits are entangled, when you have a system of qubits, each of their outcomes depend on one another. Now, in a normal computer, when you have, say, 2 bits, okay, 1 and 0, take 1 and 0. If I change the first bit to a 0, that would make it a 0 0. The second bit does not change. The second bit is independent of the first bit. But in a quantum in the quantum computer, if you have 2 bits in a superposition, that means that one bit is dependent on the other bit, and there is some condition behind them, some logic behind them. I think the most basic way to express this logic is that if your qubit 1 is of one state, then the qubit 2 has to be in the complement state. So if qubit 1 is 1, then qubit B has to be 0. So that is a little how quantum superposition works. Let's say that you want qubit B to be 0, but qubit B is 1. So you'll use another bit. You'll change that. Let's say you make qubit 1 into a 1. Let's say it was previously 0. You make that into a 1. That will automatically change qubit 2 into a 0. Now, there's a question about what would you do with that bit you changed. Maybe it also had a part to play in the computer, and maybe its changing caused a chain of reactions. Now, the basic idea is that you have to eliminate these chain reactions, right? You have to change them in a manner that changes that bit without the rest of the computer becoming faulty. That is just generally how error correction works, and there's many other ways to do it, which are pretty complicated. And thing is, we do not know which method exactly Google used, but we just know that it works. We'll trust them on that. So this is the latest progress on the field of quantum computing, and progress is pretty slow. So whenever any such new chips or any breakthroughs do come out, I will make sure to inform you, as I really have an interest for quantum computing, and I see it as the last step for humanity to develop AGI. Basically, like if you're developing artificial intelligence which would be capable of learning by itself, you need a lot of processing power. And if we are able to make quantum computers, right, if you are able to make them pretty powerful, right, way powerful than Willow, then yes, we will be able to create artificial intelligence. Basically, if our quantum computers become more powerful, artificial intelligence will become more powerful. And depending on how you see it, that would be good for us or that could be bad for us. It's personal preference. So one big disadvantage of these quantum computers getting powerful is that if they fall into the wrong hands, that's also something I discussed in a previous video. If they fall into the wrong hands, then this extreme processing power could be used against ordinary people. Basically, quantum cryptography, right? That is a theoretical method of securing passwords, right? Thing is that you need quantum computers to implement it, and you also need quantum computers to break that down. So it just depends on who gets there first. So this is obviously an progressing field, and when updates do come out, I will make sure to inform you. So that's all for today. I hope you enjoyed this video, and let's see what else goes into. Let's hope that let's hope that they make a better chip that does not fall into the wrong hands. Thank you.